Okay, so before we start here, I'd like to talk about the concept of reflections. And basically, global illumination is all about reflections. But when light basically hits a surface, it can do one of two things. It can either bounce off of the surface or it can go through the surface. And if it bounces off the surface, it's called a reflection. If it goes through, it's called a refraction. But global illumination is primarily, the concept of global illumination in CG is primarily dealing with the concept of reflection. But what's different about it is that when it reflects, it can do different things. So let's basically look at the concept of what happens when it hits a surface. We'll do this first by looking at a single ray reflection, which is how we are used to seeing reflections in CG. And basically, a ray comes in and it bounces off of a surface in an angle that's basically a mirror version of the angle that it is hitting. So that's called basically a single ray reflection. So in a scene, this is what that would look like on these objects. These are sort of, imagine these as mirrored boxes. This scene, just to give you a few side notes here, basically has a lot more than just reflections in it. I have full global illumination in this scene. You can start to see it actually in these the way that the shadows are being done, and I have my anti-aliasing set up very high so I can get these checkerboard patterns to look fairly even and smooth across here. So this was also done in V-Ray, which is a rendering engine inside of 3D Studio, and this what the ability of that rendering engine has is to actually burn in a rendering time here. And I'm seeing a rendering time of 4 minutes, 10 seconds. And that is actually a little bit high for an image like this. But again, like I said, I added a lot more than just reflections. I have a lot of GI and some high anti-aliasing, etc. So, but this is a good real world example of just looking at what that can be. So now let's look at what happens if we try to actually not get a mirrored look to the scene, and we want to actually give it some surface quality. So what we do is we're actually trying to blur the reflection slightly. And let's do a very slight blur on this, and we're just scattering. We're going to do a 4-ray scatter over 2 degrees. And basically what that means is that when a ray comes in, instead of shooting out just 1 ray, it's going to shoot out 4 rays, and it's going to scatter them just slightly. And what that does is it starts to basically break up the surface as we're going further back. Notice here it looks just fine, but back there, because it's so much further a reflection, it's breaking up how that looks. And that's really great because it's starting to give it a little bit rougher look. Now you can start to notice that we're starting to see some grain here. But this still pretty much looks like a mirror, and that's probably because we only have a 2-degree angle. Also notice that our rendering time has gone up very slightly, but it has gone up. Let's look at this now. Is if we take the same 4 rays, and instead of scattering them over 2 degrees, we scatter them over 10 degrees, so we get more of a blur. And what that does is this will start to look like this, and this is great because we now really start to blur it. It's giving that defocus look that is so important to what we're trying to do in terms of getting a rougher look. But it looks like this was basically sanded with very rough sandpaper because there's so much grain in here that it's got a real rough look to it. And we should be able to get this amount of defocused look, but not have all of this grain as if it was sanded with very fine sandpaper. And also notice that our rendering times have gone up slightly again by doing that. Okay, so now let's just add more rays. And what we're doing is we take the same 10 degrees and we add 16 rays now. And as this light bounces, it gets a lot more rays. And so what that does is it starts to really break down the surface better and create less noise. We still have noise, obviously, but it's a lot finer. So we're definitely going in the right direction. But at what expense? And the expense is rendering time. We've gone up. That was the biggest jump of all. That takes us to 8 minutes and 10 seconds in terms of rendering time. Let's push this even further, and now we've gone with 16 rays. Let's go with 64 rays of scatter. So we're taking this and we're bouncing off this surface, and we're going to bounce 64 rays of scatter, and the grain is almost completely gone. This is really looking like it was done with fine sandpaper, and but our expense, of course, was rendering time. Look at that. That is 18 minutes 44 seconds. So this becomes somewhat of a problem. Okay, so let's take a step back before we do that and start talking about the different types of reflections that exist in a surface. So surfaces basically have two types of reflections, or two types of reflection that we're going to talk about, and it's specular reflection and diffuse reflection. And when we talk about specular reflections, what I'm basically saying is that a specular highlight is actually a reflection of a very bright object. And so basically what's done in CG is that specular is actually a fake reflection of a CG light source. And that's done to be able to accomplish it very quickly and give you specular highlights without necessarily doing anything special. So let's look at this model here. Now what this is basically looking at is a very glossy looking torus, and I've created a specular highlight using traditional methods. This is a blend shader, and there's actually just a specular highlight of a light source over here. Now in CG, we accomplished this in the shader, but what that really is basically the light source that's out there. And this is accomplished very quickly without any special treatment at all. But what if we were able to take this and create a reflection of instead using a reflection method rather than a specular method? And that's what this is. And basically what it is now all I've done, instead of actually doing it through a specular model, the light source is actually reflected in here. And I've made this 100% glossy, so this is why it's so sharp. And that's my light source out there that's being reflected. And it's reflected back in this environment. There's a few other things to note. One is that this is, I'm using a Fresnel fall-off for the reflection. And what the Fresnel fall-off is actually the physical property at which reflections work in nature. So what I'm doing is, what Fresnel basically says is that reflections at glancing angles, such as along this edge right here, are much higher than they are on the surface. So they reflect more along this edge. And but you're noticing that the light source actually looks like it's 100% reflected in this area, even though it is not at a glancing angle. And why is that? Well, if you notice, actually, Fresnel reflection does not completely go away at angles that are perpendicular to the camera, so or parallel to the camera. So what that means is that in order for that to reflect as bright as it does, it actually has to be much brighter than 1, and that's exactly what it is. Light sources are very, very, very bright in real life. I mean, this is white and that's white, but that's much brighter than that is. So that's why you're able to get this, because even though this is getting the reflection is getting completely multiplied down, it's still able to reflect it completely because it's so bright. Okay, so now let's go to back to the traditional CG specular model, and we're adding some glossiness to this, glossiness or roughness to actually counteract each other in terms of terminology. But basically what we're doing is now adding some glossiness to this, or some roughness to this material. And what that basically does is blooms out our reflections of our light source and just creates this big splotch here, which is exactly what we want in terms of creating the rougher look. The advantage, obviously, is that this renders very quickly and it's able to accomplish it, and we're able to get our look very quickly. But now let's take this concept and apply that to the reflection model. And what that does is results in this. Now, we're obviously getting our bloom here. It's not quite the same, but it's pretty close. I mean, I could have obviously do a few settings to get it closer, but what it does is it blurs out our light source as we would expect it, but it's added quite a bit more, and you start to see it here, along this edge here, and let's look at it side by side. And this is mainly based on two things. One, that it's reflecting back our environment in there, and it's using the Fresnel fall-off to do it. And by doing that, not only are we able to get our light source to look just like we would expect it to, but we're actually able to reflect our environment right along the edge here in a nice scattered manner, and as well as this top here. It's really, and this is completely lacking here. And if you look at the traditional CG, look at down there, it's all black, and here we get the reflection back of the environment, and this is correct. And how that edge now starts to blend into the environment because it's reflecting it, and there is perfectly sharp. This is something that we normally try to accomplish in compositing, and here it's given to us free. But the problem is, as we've been going through this chapter, is that this is at the expense of rendering time. So what are we going to do now? Okay, so now let's take this model and apply it to diffuse reflections. And basically all a diffuse reflection really is is you take that angle at which the lights are reflecting, let's say, well, this is one particular way of doing it, but let's take that angle of diffuse reflection and scatter it over 180 degrees, basically a hemispheric dome. And what that does is, because we're using much larger angles, we're going to need more rays. And the more rays we throw at it, the cleaner the results we're going to get. But also, the more rays means longer rendering times, which can be, as we know, is a real problem. But we'll talk about the solutions in a bit. But let's just sort of look at the concept of diffuse reflection. And so now let's basically take a reflection model, and we're going to reflect 16 rays, hemispheric rays, off of a surface, and that's going to give us our diffuse reflection. And let's look at this particular scene here. Now, what's going on is basically that a ray comes in and it's reflecting back, and if this is, we're going to talk about ambient occlusion a little bit, but this is basically an ambient occlusion model, and if there's a sky, the sky that is lighting up everything in this area. So basically, light is coming from all direction. But if under here, it can't really see much sky, so it basically is reflecting black because it can't really see much. But there's a few rays that are, glancing angles. They're just barely getting out, and it's creating, it's able to capture the thing. So the way that it looks is basically it's the very diffuse lighting, which is what it's called. And a few other things to note on this. In order to give a true rendering time examples, because I know that a lot of people are interested in the effects of this, I've actually rendered this without anti-aliasing. So I'm just doing a pure diffuse scatter with no anti-aliasing, so that's why you have this edginess here. But this, using a Monte Carlo system, this was actually able to render in 33 seconds. So it's very fast if you turn off all the whiz-bang stuff on it, which is pretty good. But very, very grainy image, only 16 rays. So now let's take this again and take it up to 64 rays, which is, obviously about, 4 times as much, right? So 4 times many more rays should look a lot smoother. In fact, it does. That's great. So now we've already started to get rid of all of our noise in this area, and it's starting to, not all of it, I mean, it's reduced quite a bit, and it's starting to look a lot better. Rendering times have gone up, 1 minute 43 seconds. Okay, so that's already our first hit. And let's push this even further, and let's take it up to 4 times as many more rays again. So let's go to 256 rays, and now it's much better. There's still much grain here, but let's see if we can even push this even further and go from here to 4 times as many more rays again, and we'll go to 10,024 hemispheric rays, and that's obviously a much larger scatter. And at this point, there's no noise. I mean, there's imperceivable amount of noise. You would really have to try to find it by doing some serious gamma shifts to be able to find the noise. But the expense is now we're at 25 minutes to render this, and that is a big problem. So as I said, I kind of turned off all the anti-aliasing just so we could just look at the hit. So we went from 33 seconds to 25 minutes, which is a big difference. So the big problem is that when we start to get these smooth look, we sacrifice a lot. So what we have to do is we have to create there are solutions for global illumination to make them practical in the real world, and there are acceleration techniques. And that's mainly the big thing that that most people have to learn, is how to make the most advantage out of the acceleration techniques, so that you can get all of the smoothness that you're looking for without necessarily having these large rendering times. And there are many techniques that we can do that, and that's what we will look at in our next chapter.